In this lesson, we're going to examine the mole, and we're going to derive two very important relationships that we're going to use. The mole specifically is the unit that we use to measure the amount of a substance. So when I talk about the amount, it's the amount of molecules that I have or the amount of atoms that I have in a particular sample. And as we've seen previously, the amount in 1 mole is 6.02 times 10 to the 23. So this little image here, he's counting some atoms, and there are 6.02 times 10 to the 23 atoms in that sample. And so we would refer to it as a mole. So just like a dozen is 12, a mole refers to 6.02 times 10 to the 23. Now how it's defined, how 1 mole is defined as having 6.022 times 10 to the 23 particles in it, is in reference to carbon. It's defined as the number of particles that a 12-gram sample of the isotope of carbon-12 has. So if we just took a pure sample of only carbon-12 and we took 12 grams of it, that sample would contain 6.022 times 10 to the 23 atoms of carbon. Now you'll see in this image as well, I've got two different versions. We're going to use the one with 4 significant digits because we never want a value that we're going to use from a table like a constant to limit our significant digits. So working with 6.022 times 10 to the 23 will help us to report more precise values overall. We're going to be looking at two relationships, and the first relationship that we're going to derive is the relationship between the number of particles that we have and the number of moles in a sample. And I'm going to use neon, carbon dioxide, and sodium chloride as my 3 examples here. And you're going to see in the first set that I'm working with 1 mole of each of these. So I'm going to have 6.022 times 10 to the 23 neon atoms. I'm going to have 6.022 times 10 to the 23 carbon dioxide molecules. And I'm going to have 6.022 times 10 to the 23 formula units of NaCl. So there's 2 pieces here. One, the fact that I've got a mole just means that I have 6.022 times 10 to the 23 of that substance. And then depending on what I'm counting, so neon versus carbon dioxide versus sodium chloride, I'm using a different unit because I'm counting different things. It's like if I count a dozen donuts versus a dozen flowers, right? It doesn't really matter what I'm counting, but I'm going to describe it with a different unit sometimes. So in this next slide, what I'm doing here is differentiating between atoms versus molecules versus formula units. It really depends on the substance. So neon is an element and it's composed of discrete atoms when we have a sample of it. So I'm going to be counting the discrete individual atoms when I'm counting the particles. Liquid, when I have a sample of liquid water, or this connects to the example of carbon dioxide. So if I had carbon dioxide or water, that substance would be composed of discrete or individual water molecules or carbon dioxide molecules. So that's what I'm going to be counting. If I have a mole of carbon dioxide, I'm going to have 6.022 times 10 to the 23 molecules of carbon dioxide. For ionic compounds, as you know, they're organized in this crystal lattice with the positive and the negative ions being tightly packed. And so we don't have these discrete molecules. And so calling them molecules doesn't really make sense here. What we are counting is we are counting formula units. So we're counting each time NaCl appears within the sample. Or the example here, it's each time, so one formula unit of NH4Cl consists of one NH4 plus ion and one Cl minus ion. So I'm counting those discrete formula units. For memory's sake, it's just easy to differentiate when you are thinking about using the word molecules, but it's an ionic compound, you're going to use formula units instead. And that's often helpful for students to remember. So the next piece here is we want to look at, well, what if I have half a mole of neon? Okay, so if I have half a mole of neon, I'm going to have half of Avogadro's number of atoms. If I have 2 moles of carbon dioxide, to find out how many molecules I have, I need to multiply Avogadro's number by that number of moles. If I was working with a dozen, if I had half a dozen, I would have 6. So I could take half of 12. Or if I had 2 dozen, I could take 2 times 12. 0.25 moles of NaCl, I can take 0.25 of Avogadro's number. So what this is showing us here is a formula that we have that relates the number of particles and the number of moles. So if I know my number of moles, I can find the number of particles by multiplying that number of moles by Avogadro's number. And so we have the formula. Number of particles, or big N, is equal to the number of moles times Avogadro's number. And these are the symbols that we use. So for number of particles, we use big N. Avogadro's number, this symbol is N with a subscript of A, and we know that that value is 6.022 times 10 to the 23. The symbol that we use in chemistry for the mole is lowercase n. What I have here, and this is also in your notes, is the triangle version of this relationship so that you can convert between them. Ideally, you're using the formula moles is equal to, number of particles is equal to number of moles times Avogadro's number, and you're rearranging it for what you're finding. But this is also a helpful tool just if you want to set it up for yourself so that you can rearrange it without making an error. So, and how these work is you cover it up. So if I cover up this N, the big N, which is my number of particles, I might be counting molecules or formula units or atoms or potentially ions, for example. I'm going to take my moles and I'm going to times by Avogadro's number. Okay? And Avogadro's number is our number of particles per mole. In the next series of lessons, you're going to be looking at some examples, practicing using this formula. The focus of this lesson is just the derivation. The next relationship that we want to examine is the relationship between mass and number of moles. Because in the lab setting, I'm not going to be able to actually measure on any kind of a scale, or I don't have any tool for counting individual particles, but I want to be able to measure quantities and know how much stuff or how many atoms or molecules or formula units I have in that sample. And so we need a mass relationship. We need to know how many grams does it take to have a certain number of moles. And as we saw from the definition of the mole, 1 mole of a substance is defined as the number of particles in a 12-gram sample of carbon 12. So carbon 12, okay, in this, if I have 12 grams, then that is going to give me 1 mole of my sample, okay, of atoms of carbon. So this mass that we've been using as our atomic mass unit, it now serves 2 purposes. If we want to count protons, electrons, and neutrons, we're thinking about it in atomic mass units, which is a really small unit of measurement. But now what we're going to be using it as is as what we call the molar mass. And the molar mass of a substance is the mass in grams of 1 mole. So if I want 1 mole of carbon, I need to obtain 12 grams of it. If I want 1 mole of magnesium, or 6.022 times 10 to the 23 atoms of magnesium, I'm going to need to get a 24.31 gram sample. And this will also translate, you'll see in a moment, we're going to work with neon and carbon dioxide and sodium chloride again. And we're going to need to tally it up. So if I have sodium chloride, the molar mass of sodium is 22.99. The molar mass of chlorine is 35.45. So what I'm going to need to do to find the mass of 1 mole of sodium chloride, or NaCl, is I'm going to need to add these 2 together. So if you refer to a periodic table while we look through this, it could help. So if I have these amounts of moles, I want to determine the mass of them. The first thing that I'm going to do is figure out what the molar mass is of each of these individual substances. So for neon, it's just the atom, so I get the number off the periodic table, 20.81 grams for 1 mole. For carbon dioxide, I'm going to need to take the sum of the molar mass of the carbon and of the 2 oxygens. This is something that you can do on the side in your calculator and make a note of the molar mass for good communication. If you need to, make a list of the atoms and carefully write out their individual masses and then take a tally, then do that. And do that for as long as you need to so that you're confident in calculating the molar mass. So for carbon dioxide, if I take that sum, I'm going to find that I get a molar mass of 44.02 grams per mole. So if I want a mole of carbon dioxide, this is how many grams I need. And finally for NaCl, when I take the sum of 22.99 and 35.45, I get a molar mass of 58.44. Now, if I have 1 mole of neon, the molar mass, the number of grams per 1 mole, is 20.18. So the mass of that is going to simply be 20.18 grams. For carbon dioxide, again, if I have a mole, the molar mass is the mass of 1 mole. For sodium chloride, the mass of 1 mole is 58.44, so therefore the mass of that is going to be 58.44. And then for the next set, if I have half a mole, I'm going to have half as many grams. So I'm going to take 0.5 and I'm going to multiply by 20.18. If I have 2 moles of CO2, or if I want to obtain 2 moles of CO2, I'm going to need twice its molar mass. So I'm going to take 2 times the molar mass of carbon dioxide. And lastly, if I have 0.25 moles of sodium chloride, I'm going to need 0.25 of 58.44. The reason I'm not doing the math here, you will finish the problem and do the math and report your answer to the correct number of significant digits. But the point here is that we're trying to derive the formula. So we want to see, if I want to find the mass, what do I need to do? I need to take the moles of the sample and I need to multiply by the molar mass. So to find the mass in grams, we're going to take mass is equal to moles times molar mass. We've already seen the symbol for moles being N. Mass is a symbol that you've probably seen before in previous courses, but if not, then you can kind of see it here. And then big M is the symbol that is traditionally used for molar mass. Okay. You'll see that sometimes in my videos, because for a long time I used MM. Okay. It's the same, molar mass, MM, or big M as the molar mass. Now, traditionally, we actually rearrange this formula and we communicate and often talk about this formula as moles is equal to mass divided by molar mass. And that's just simply a rearrangement of our derived formula. When we want to put this into a triangle, this is going to have to be in the bottom left, the top, and the bottom right. Okay, so we've got our triangle here. If I want moles, I cover that up and find mass over molar mass. If I want to find mass, I cover that up and see that the formula is moles times molar mass. And finally, if I want molar mass, it's going to be mass divided by moles. Now we've got 2 relationships here. We've got our first one, which related the number of particles and the number of moles. And then our second one related the mass and the number of moles. And this here kind of gives us the view of the mole being our central unit that's ultimately going to relate the mass to the number of particles, or in this description, the number of atoms. And you might be thinking, oh, well, I'll just make a third formula and I'm going to relate number of particles directly to mass. And we don't typically do that in chemistry because the mole is so central to what we're doing that we don't ever want to just use a formula where we lose sight of the mole as being this central unit. Okay, so if you want to, and you'll see this in the practice, if you want to go from mass to number of particles, you're actually going to go via the mole. So you'll find the mole first and then find the atoms. And the same going the other direction. The last little bit here, which is a little bit extra at the moment, but it's a bit of a preview, is that sometimes we'll actually be counting the atoms when we're working with molecules. So say, for example, I have this CH4 molecule as the image presented on the left. The number of atoms in that one molecule is 5, right? So if I know the number of molecules that I have, I can figure out how many atoms are in the sample by multiplying by the atoms per molecule, right? So if I had 2 of these, 2 molecules, there's 5 atoms per molecule. So I would have a total of 10 atoms in that case, okay? And if you've got the moles of the atoms, you can obviously find the number of atoms using Avogadro's number. Okay, so the next step here is to look at a series of practice questions where you see what you're looking for, do the calculation. You're also going to need to practice using your calculator in this unit because you need to use scientific notation properly to get accurate answers. You also need to report all of your answers to the correct number of significant digits and use proper communication when presenting your work.